Great. So we're recording now. So thank you for that, Amy. Other new participants that want to introduce themselves, no pressure. We can pick it up in a future edition as well.
Hi everyone, Mike Vinnie-Kirk from Inspire Impact based in Sydney. We're impact investors and have a particular interest in the oceans as well as many other areas across the market, but have a particular interest in the oceans and do some work with Paul on the funds and investment side of oceans as well. Looking forward to the discussion this morning.
Great, thanks, Mike. Good to have you here. Anyone else want to introduce themselves as a new participant?
Yeah, this is hi Paul. This is Frederick Anderson, member of the group Blue Ocean Exchange, and Fred Sullivan suggested I sit in because I have my interest in the Blue Ocean Exchange project. So looking forward to be a participant.
Thanks, Frederick. And that's an effort we have going on regarding bond development, blue bond development. So who else was going to jump in there?
Yeah, hi everyone. I'm Rob Clark. I'm with a company called Ionata. We have a carbon capture technology that we're introducing into the marine world because it's very small and mobile for carbon capture on ships. It's not particularly ready for long ocean haul ships yet, but we do see an excellent market for coastal feeders, ferries to actually get a zero carbon. Well, these ships transition to zero carbon fuels. So it's a kind of technology that's ready and available now to make a difference. Well, as I say, the ultimate goal is transition to zero carbon fuels.
Great, thanks, Rob. Really happy to have you here. That's actually, I was having some discussions last week about the coastal shipping and short sea shipping and zero carbon. So, and I'll just apologize. There's construction going on in our house here, so there's periodically some background noise. Other introductions? If not, we'll go ahead and jump into the presentations then. And I will stop sharing, John, to allow you to share your screen and present and introduce yourself. There you go.
Okay, thanks, Paul. Let's see if the screen sharing is up. All right, hopefully everyone can see the screen. I might just keep it on that view, actually. Do you think that's okay? Everyone can hear? Yep. Okay. Thanks, Paul. So yeah, my name's John Ridley. I'm a biologist by trade, originally from the UK, moved to Australia in the year 2000, and Ocean Nourishment was set up in the year 2004 when we realized that we're heading for a climate crisis. So just to give you an idea of the mission of the company, it's to pioneer the restoration of the open ocean ecology to achieve multiple ecosystem benefits. So we're really focused on three things. One is to drive large-scale carbon export to the deep ocean using biological processes. Secondly, it's to increase marine pelagic fisheries in certain parts of the ocean. And the third one is to reduce the surface ocean acidity, so moving acidity to the deep ocean. So the CDR pathway that we're looking at is the biological pump in the ocean. I think these diagrams are great because I don't know what it's like where you are, but in Australia, there's a real emphasis on the soil sink, soil carbon. That's that little box there, if you can see the cursor moving. So 1,500 gigatons, but we're more interested in this sink, which is 38,000 gigatons. And we want to move carbon from the atmosphere through the surface ocean into this deep sink through phytoplankton. So this happens naturally, and we just want to enhance the process to increase the drawdown. It's already very significant. So just an overview of the process. So we're really interested in the nitrogen limited areas of the ocean. So this, starting from the top left-hand corner, this image shows that the ocean is primarily limited in its ability for primary productivity by nitrogen. That's those pink areas. So these are the areas that we're interested in. The polar regions are sort of high in nitrogen nutrients and phosphorus, and potentially limited by iron in the polar zones. So 60% of the ocean is suitable to ocean nourishment. In terms of like scalable technology, we're really looking at the hydrogen market. So using wind energy in the ocean, particularly wind energy at night, which is often not captured, and switching that into green ammonia, which would be our source of sustainable nitrogen. And to that, we would add certain micronutrients, which would create our ocean plant food. So that's a mix which is primarily nitrogen. Nitrogen's the key driver, but various micronutrients play a role as well. And then we disperse that into the surface ocean from ships into the deep ocean at a rate where 1 ton of the plant food would sequester 14 tons of carbon dioxide. So it's quite a high transfer rate for carbon drawdown. And the design level for chlorophyll is 4 micrograms per meter square. This has often been confused in literature. So that's well below the chlorophyll levels that you would see in, say, a nutrient upwelling, a natural system. The upwellings are much higher than that. So when you're doing ocean nourishment, you won't see it. Yeah, you'll pick it up from satellite and things, but it's actually a fairly small effect on surface waters and the marine environment. When we did an environmental impact assessment for one of our proposed trials, we couldn't find any impact. It's hard to trace the impact in the ocean. So you're growing phytoplankton. These are diatoms. It doesn't really matter what phytoplankton you're growing. They grow very quickly, 5 to 7 day cycles. So they're sitting in the surface ocean. They're limited in their growth by lack of nitrogen. You add the nitrogen, so you increase the numbers of phytoplankton in the surface ocean. As they die, they drop down into the deep ocean. Small amounts go through straight through the thermocline into the deep ocean, where they're stored almost permanently for 1,000 years. And a lot of it is remineralized in the surface ocean, re-releasing the nutrients, re-releasing the carbon, and the process cycles. This is an important point about ocean nourishment. It goes through multiple cycles to get the carbon down, but the nitrogen is all consumed. So there's no nitrogen that's left over. It's all completely consumed. And in terms of accounting for the process, you can use satellite technology to track the plume and potentially measure the amount of carbon which is created and hence exported. And we're also looking at in situ techniques for measuring the captured carbon as it falls through the ocean. That's just an outline of the overall process. So the site economics, I'm sorry, drink. So we're a technology company. Our aim is to license sites. We're not trying to do this all ourselves. This is a big undertaking looking at ocean carbon. So the sites are deep water sites. Ideally, they're 1,000 meter deep. So this doesn't work in shallow coastal waters. It's a deep ocean process. So rules out quite large areas of, like the North Sea, for instance, which is just a shallow pond. It's totally unsuitable for this type of process. And it's ship-based, so you're doing it from ships. It could be, you could have fixed moorings in the sea, or you could be using ships as they traverse the oceans. The initial area of influence is about 20 kilometers. And as I mentioned, 1 ton sequesters 14 tons of carbon dioxide. So it's quite a good ratio. So your site numbers are, if you have 3 ships operating for, say, 260 days a year, it's about 6 million tons of CO2 per annum sequestered. And with carbon credits at $50 a ton, that's probably not where they are today, but that's where they will be, you would imagine. That's a revenue for the operator of about $300 million US per annum. And the carbon permanence is high. It's up to 1,000 years. Process cost is still $20 a ton US. And there's a lot of potential co-benefits. So in the right areas, particularly where you're looking at extending upwellings, which is a key for our site development, looking at upwellings and how you could extend their zone of influence, you could get fisheries. So our estimate is 114,000 tons wet weight of fish per annum. And finally, the other co-benefit is moving that carbon from the surface ocean to the deep ocean also removes some of the acidity. So there's not many techniques that also address ocean acidification, which is obviously an emerging problem for the whole biodiversity of the ocean. So just in the footnotes there, it can be a pulse process or a continuous process. And this is important in how it affects the ecology. If it's a continuous process, the ecology will adapt to the extra nutrients and the extra life that's created. If it's pulsed, it'll create movements of ecology continuously adapting to the new environment. The sites are both within the EEZs and also can be open oceans. And this is all subject to international approval by the International Maritime Organization. So they are the regulator, if you like, for ocean nourishment. In terms of the Sustainable Development Goals, I think we'll increasingly see that meeting any of the Sustainable Development Goals without addressing climate is virtually impossible. Certainly in Australia, we're coming to that realization. So SDG 13 on climate action is obviously the most important one, but life below the oceans, SDG 14, yeah, without a sustainable functioning ocean ecology, we're really struggling to sustain ocean life. And then again, in terms of food security, you know, if we can increase more food from the ocean where we're just hunter-gatherers, that's got to be good for poverty and zero hunger. So the ocean is just being treated as a take-all situation rather than a managed situation. So there is the potential to manage the photosynthetic potential of the ocean. So I just want to show you some of the sites that we're looking at. So mostly we're following the nutrient upwellings and we're in the low nitrogen waters. So we're limited in latitude. So here we are in Sydney, can't go much lower than that. Although northern Tasmanian waters right down here is starting to change and be more nitrogen limited. So the ocean is in a constant change. But if you look at sites over here, this is the Peruvian anchovy upwellings here. Off Morocco, we've done a lot of work. There's 3 upwellings off the coast of Morocco. Similar characteristics in Somalia and Oman, and deep water trench off Japan, a very interesting area. South China Sea, and the Northwest Shelf in Australia. It's a very nutrient poor area, but it ties the process to a gas extraction and potentially the hydrogen market. So these sites are sort of carefully selected. These are more the regions than the actual sites, based on a lot of site characteristics. So we've just published a paper on how we selected this site in particular. So if anyone's interested, they can delve into the detail of how you go about looking for a site. So the unique selling points for ocean nourishment, we have a process that partly addresses climate, declining fisheries, and ocean acidification, which makes it interesting. It's a technology that could capitalize on excess wind power, the emerging hydrogen market, and green ammonia to drive ocean restoration. It's patented, so we have a number of patents over the years. We have patents around the methodology for accounting for the carbon. Actually, we have two method patents and a process patent, which is carbon sequestration using a floating vessel. So that's quite a broad patent. If you want to use nitrogen to stimulate the biological pump, that's what that patent covers. The global potential. So the global potential of ocean nourishment is about 1 gigaton of carbon per year at its full scale. So this is based on the amount of excess phosphorus really that's sitting in the surface ocean. At some point, if you do this heavily, you'd run out of phosphorus and you'd have to add phosphorus. So just using nitrogen alone, it's about 1 gigaton of carbon per year, and that's about 1/10 of the current emissions problem we have today. So it's certainly off scale. It could be utilized obviously for smaller scale ocean restoration, could be fish recovery, or it could be carbon drawdown in other parts of the ocean as well. Our timeline, it's been a long journey. It's a technology that was developed in Sydney University. So this idea of ocean nourishment's had more than 20 years in academia, principally in Sydney University. We established the company in 2004. We were featured on the BBC's 5 Ways to Save the World documentary in 2007. We played an active role in the UNFCCC COPs, particularly Poznan and then Copenhagen, before things started to fall away on the carbon markets. We've raised about 2.5 million. We've been a member of the World Ocean Council since 2012 and presenting on blue carbon and ocean carbon for almost 9 years now. And we've written all the core technical papers for ocean nourishment. So we have a strong technical basis for it. And now we're looking to raise Series A capital. The team, we've got an experienced team. Murray Scott, who's the finance director. Peter Wien's the chairman. David Rizik's our technical director. He's a scientist who's published widely on phytoplankton. And Professor Ian Jones is the inventor. Just quickly, our roadmap, the key things that we need to do over the next 5 years: independent review of the technology of ocean nourishment. And we're talking to a number of different marine institutes and government organizations about that. And then establishing a semi-permanent demonstration site. This needs to probably run for multiple years, I think, because that's one of the problems in this area is it's been confined to short experiments that don't give you enough data. So that's what we're looking for, a site that can run for 1 to 2 years, build up the data set, have full ecosystem modeling to de-risk the whole process, and then move towards the methodologies of how it could be accounted. And obviously IMO we need to have approval from the International Maritime Organization for this to move to commercial activities. So it's only approved for research at the moment. In terms of finance, we value Ocean Nourishment Corporation at about 9.4 million. And we've got 2 capital raisings to allow shareholders to come in at any level, but also to look for a partner shareholder who would take a 30% stake in the company. And I'll leave it there. That's thanks for listening, and I'm happy to take any questions.
Great, thanks very much, John. Very, very well organized, concise, and to the point, and great to see the progress being made. So let's take a bit of time for questions with John, and then also at the end of the 3 presentations, if there's some more collective discussion to be had, certainly we want to make time for that. So the floor is open.
So Phil Kithill here. John, how is the ocean acidification? What's the actual process that you envision for drawing down surface, changing the pH in the ocean surface with your technology? I'm not quite following that.
Yeah, that's a good question. It's just through the biological pump, so it's not a great scale. So you're moving that carbon from the surface to the deep ocean. So in effect, you're not solving the ocean acidification, probably just shifting it. But you would have to do you'd have to enhance the biological pump at quite a scale to make that measurable in terms of pH. But it's conceivable.
But you'd get CO2 dissolving into the ocean at the same time, so it'd be essentially a zero sum, you think?
Look, the atmosphere and oceans are always going to try and go to equilibrium, isn't it? So yeah, we have to bring down those atmospheric levels to reduce that equilibrium. So yeah, this is probably a 50, 100-year project, really, if we're honest. So we may not be on Zoom by the end of it.
Phil, I don't think it's a zero-sum game. I think you're actually drawing carbon out of the surface by enhancing the biological pump. So there's a net export out of the mixed layer into the middle and deep ocean where there's enormous capacity for more carbon. I mean, you could store the entire carbon assets of the atmosphere 45 times in the middle and deep ocean just with the existing concentrations. So, I think that's an example of how the export is highly valuable.
If I could just ask you a question, John? Are you familiar with the carbon ice concept that is being worked on by, I believe it's DNVGL, Vale, and a few other large shippers, where our system is mainly for short haul right now, where we capture the carbon on board the ship and then take it off and put it into a sequester pipeline or a utilization opportunity. That amount of carbon capture, because you have 3 tons of CO2 for every ton of fuel burnt, isn't viable for long transoceanic voyages. So DNVGL looked at saying, okay, we can turn it into carbon ice, basically, and then bring it to a sequester site, somewhat as you described, and these ice pellets will then drop down and sequester into the seabed.
Oh, interesting. Yeah.
Would it be interesting, to have this if there's a test site, to have it co-located?
Yeah, I think
So-
with the test site, I think for any of these demonstration sites, we have to maximize the range of technologies that can be tested. So I think that would be a good idea. And yeah, we talked to Vale actually about sequestering carbon from their ship routes. So yeah, that would be interesting.
Yeah, to combine the two. And as I say, right now, we don't have a solution for deep ocean transits, but we do have a solution for coastal transits where we can capture and then remove. So it'd be a huge movement forward because of, these ships burn 100 tons a day for the large ships.
So how do you get the ice into the deep ocean? You just pipe it?
Well, the idea was you just form these sort of bullet-shaped pellets, and the density of these just drops them down, and they'll. The theory, at least, is that they'll bury into the seabed substrate quite deeply, and be captured there. I don't know too much about it, to be honest.
Yeah, that sounds interesting.
We've got Francis has her hand up, and feel free to either signal manually or with the electronic hand up. Francis, over to you.
Great. Thanks. And thanks, John, for the presentation. Could you explain a little bit more about your kind of permitting journey, and what are some of the challenges you face, and some of the details that you could share with us?
Yeah, so it has been a long road. So when we started, there was no guidance or international framework for trying to work with the biological pump in the ocean. So the IMO took this on board. I think it was around about 2011. They produced the guidelines for the research, but they limited commercial activities. So they're saying you can't do this for commercial gain at the moment. But this is all guidelines only. It's not legal. So it's an interesting, because it's all under the London Convention and Protocol, which I think there's 57 countries, and they need a certain number of countries to agree to make it legally binding. So that's what they're working on, but I don't think there's an appetite to make it legally binding at the moment. I think they would prefer to have it as a guidance. So while all that was happening, a lot of the university research was curtailed. So that's why in the last 8 to 10 years, we haven't seen many experiments in the ocean, it's sad. The science was held back over the last decade. So there hasn't been any at-sea experiments of significance probably in the last 8 years. So now if you want an experiment, you need permission. So we would need permission in Australia from the government at a federal level and at a state level. And then we would need the IMO to say, to give their blessing or approval as well. And it's a bit complicated because it's guidance, and it doesn't strictly apply to the high seas either. But I think at least there's a framework coming together for how we can govern this sensibly.
Thanks, John. Antonius.
Hi, John. Thanks for the presentation. Could you just say a few more words about how you come to the estimate of net carbon sequestration, net downward movement of carbon?
Yeah, sure. So based on the Redfield ratio, that's how it's calculated, that the ratio between nitrogen and carbon. So we've got a we've got a whole methodology paper that calculates all the potential carbon losses from the process and all the gains, and the gain in the ocean, the net gain works out to be 1 ton of our ocean plant food to 14 tons of carbon dioxide sequestered. So it's all based on the Redfield ratio and how these elements behave in the ocean. Yeah, I could send you a copy if you want to delve more deeply into the methodology. We've published it actually, so it's in a peer-reviewed paper.
Yeah, I'll look it up. Thank you. I guess my question is getting also a little bit at the question of permanence, and
right,
if you want to link the sequestration to the carbon market, then I think the barrier is quite high to have to prove that permanence, right?
Yeah.
And for iron fertilization, it's been so difficult to really establish under which conditions and in what parts of the ocean, what kind of a sequestration you'll have, and then also what the permanence of that sequestration is. So it would be interesting to hear a little more about to what extent this has been calculated versus also measured in mesocosm experiments and similar settings.
Yeah, look, there has been only mesocosm experiments. There hasn't been any real scaled ocean experiments. But the key difference with nitrogen and iron is the multiple cycling in the ocean. So the iron fertilization essentially has one chance, one growth of phytoplankton to drop that carbon into the deep ocean. And then you have limiting nutrients straight away, you know. So with the nitrogen process, you've got multiple cycles. You get phytoplankton growth, carbon dropping down, remineralization, nutrients recycling, and the process just cycles through the ocean. So over multiple cycles, you get that carbon gradual drop down. Of course, we've got to prove that that carbon's getting below the thermocline into the deep ocean and therefore is permanently stored. But that's the biological process, you know, so that's what's happening naturally. So it's a question of just verifying that that's the case. And the permanence, we believe, is about 1,000 years once you're in the deep ocean, and those nutrients will be upturned eventually, and they'll start the cycle again. The carbon will come back and the nutrients will come back and the process will carry on.
Yeah, so just following up on that, for several decades, oceanographers have been measuring the net carbon flux with particulate organic carbon through 500-meter depths or other depths. And so that methodology is well established. Now, assuming that all of that carbon is then remineralized by microbes, then you really measure the time to outcropping of that water body, again, at the surface, typically in the Southern Ocean. And that time scale is measurable at 100 to 4,000 years. And so there is a well-established ocean conveyor model that can be verified through radiocarbon dating of deep waters. So there is a well-established methodology. And of course, the United Nations with the CDM has established 100 years as a threshold, but the ocean conveyor is typically a 4,000-year conveyor. So depending on what part of the ocean you're working in, centuries to millennia is practical.
Yeah, thanks, Brian.
Pleasure.
But I'd like to thanks Brian for that, and thanks John and the other interventions here. Good discussion. What I'd like to do is move on to Jeff and C Combinator. And so John, if you can unshare, and then Jeff, you can go ahead and share your screen. And what I'd like to do is also encourage those of you on the finance and investment side to be thinking about your role in this and your questions, and maybe in particular at the end we might have some more cross-cutting discussion about the finance and investment context and dynamics here. But Jeff, we'll for now we'll go to you, and looking forward to hearing about C Combinator.
Great, thank you, Paul, for the invitation. Thank you, John. Fascinating ideas there. And so we're pleased to be a part of this conversation. Everybody's good with the screen share, I presume. Thank you. So C Combinator, we hope to be, and soon be, we're aiming at being the lowest cost, most scalable, and most sustainable biocarbon capture, usage, and sequestration company in the world, BioCCUS. Because what we're doing is we're taking waste sargassum, which requires no land or inputs, and this is the seaweed inundating the Caribbean now, of course, from the Sargasso Sea as it floats across into the bays, causing destruction. We're taking that product, which has been very difficult to deal with for reasons of arsenic and other reasons. We've figured out ways to make very high value products out of it to make it worthwhile to capture. And so we can create all kinds of products and sequestration methods along the way. It is the largest bloom in the world, and it's starting to capture a lot of attention over the last 5 to 7 years. It's become enormous and is causing all sorts of tourism and jobs harm in the Caribbean islands. We think of ourselves as the opposite of an oil company, because what we're doing is, while oil companies have extracted oil from the ground, created lots of needed products, they've also created a lot of emissions. And what we like about our model is sargassum itself absorbs carbon as it grows by itself on the ocean, with, of course, enough nutrients needed. But in a lot of places, it has that. In large part, it's fueled by the nitrogen and phosphate coming out of the Amazon basin as the rainforests have been converted to farmlands. So all of that nutrient is really a pollutant in the ocean at a certain level. And the sargassum uses that, plus, of course, absorbs CO2 and lands on these beaches. And so what we're doing is collecting it around the Caribbean, turning it into everything from plastics to packaging, textiles, cosmetics, and all kinds of agricultural usages. So, and then when we look at ways to both avoid methane on the beach, so if it just sits there and rots, it methanogenicizes into copious amounts of methane. We avoid that because it doesn't go into a landfill. So that's a carbon credit as well. We create products out of it, and then we pay attention to the end of life of those products. So trying to make them biocompostable, compostable in the ocean but degradable in the ocean with no additional temperatures needed beyond the normal ocean infrastructure and environment. And we're looking at ways to really play into a whole bunch of products in terms of coking coal substitutions, which is a massive 8% of all global emissions. We possibly could be a solution for that. And we're looking at microbial usage of it. So taking gene editing combined with AI on the microbe selection and actually turning it into plastics or biofuels. So this is an example of the problem. It has arsenic and creates anoxic environments in the bays when it builds up. Of course, in the open ocean, it's highly useful and it even promotes biological diversity in the ocean, but it becomes harmful when it piles up. So we found a way to make the green out of sargassum. Our primary products are these green ovals, and that we're pulling out. But I'll just point out that the end markets are enormous. So our focus is how do we prioritize our end markets to the most valuable, and also as part of our mission, having the most carbon impact and ocean health. So the top ones there, hydrogels and aerogels, we have patented technology that is allowing us to both treat the arsenic and the other components of the seaweed, but then also create hydrogels and aerogels in a way that is about 1/10 the energy and half the water as traditional alginates and other products have been made. So our hydrogels and aerogels are getting a lot of attention as the EU has eliminated microplastics. So we're talking with high-end consumer cosmetics companies about replacing their petrochemically based hydrogels in lotions and creams, but also using the aerogels for insulation. I'll show you those products in a minute. We really have this biorefinery process that takes all these products on the left and turns them into high-use products. So in the past, there hasn't been a lot of progress with sargassum because people are trying to make bricks out of it or fertilizer, et cetera. It's limited use cases. But now we think we're opening up a whole new set of markets with hydrogels and aerogels at $200 a kilogram. And that can really be at the high end. And then also there are fucoidins, fucoxanthins, and laminarins, which can be extracted from sargassum for the health markets as well. But we try to think of our business as really addressing about 8 of the drawdown solutions, including making bioplastics, biochar, and ag management. So I'll give you a quick sense of that in a minute. This is some of the problem is we're based in Puerto Morelos, which collects about 74% of all sargassum ends up there in the backstop of the Caribbean. We have a team that has collected over hundreds of thousands of tons a year. We have the capacity to collect up to 1 million, and we can augment that quite easily. We get paid by the resorts to collect this product off their beach. We then dry it, we process it. We have biostimulant for crops, which is left in Mexico. The dried seaweed pulp that remains is shipped to Puerto Rico, where we have the full support of the Puerto Rican government as well, where we're building this large-scale processing plant to turn it into these products. I'll just note that the Mexican government asked us recently to write the protocol for how to collect sargassum on the beach, about which we're quite excited. And the Navy is bringing us all of their sargassum for this foreseeable future, because they're pleased that someone's doing something with it instead of treating it like a cost center. So these are some of the roadmap to how we build up to the different products. You'll note the aerogels and hydrogels, all kinds of applications of products. I'll show you those in a minute. We have LOIs across all these industries with customers who are looking for ways to both meet their sustainability goals and to diversify their supply chain. I'll just point out that one of the reasons why people are talking to us at large scale, so like an $11 billion packaging manufacturer is talking to us because they've wanted to move to more sustainable sources, but have not yet found enough supply. It's hard to find enough seaweed supply to be talking about 100,000 tons a year of product. But in this case, we can do that. So we've loved that, and we've loved that we can think about these higher value products as well. This is our aerogel product, where we're looking at applications for insulation, clothing. So you can imagine it could replace goose down. We know that the thermal resistance is approximately the same. We're working with a couple of big clothing manufacturers, and also really creating fake leather, fake silk, wool, and these hydrogels. You see these aero beads. These beads can soak up moisture and hold up to 200 times their weight. We're looking at ultra lightweight aerogels as well, which can really play in a lot of the insulation markets where weight really matters. And so these products can be tuned. We essentially we built a platform so we can actually tune the characteristics of any product to these buyers' needs. We're also, one of our first products is we're looking at shoe soles. So we're partnering with manufacturing companies that provide products to a lot of different big brands we've all heard of, and they are manufacturing for them. So one of the easy ways to get into this market is to say, well, you tell us where each of these products fit. And so we've really made some great progress with that. We're working with a company that has a lot of implications with shoes, some big name shoe brands, and clothing brands, textiles. It's essentially a replacement rubber. We also are pretty excited about the hydrogels. So these hydrogels absorb water. You can put them on fields, and they will, in the case of a rainstorm, absorb up to 200 times their weight and then release it back. The orange you see in the middle there with the light behind it, we've actually encapsulated seeds in the hydrogels, and we can also put biostimulant in the hydrogels as well. So the biostimulant will help the seed germinate. We've received really positive feedback from a large-scale agricultural manufacturer in India, who says if we can do this at scale, could be game-changing. So we're hopeful to follow through with that. And then these also increase yields. That's less water usage, helps reduce drought stress, and helps prevent erosion. If you can imagine, if you have a big rain and it washes your seeds out early in the season, that's troublesome for a lot of farmers in India, Mexico, and other places around the world. We hope we can get to a lot of gigatons of carbon. This is full potential if we could, replace packaging and plastics and all that. But we're looking at a lot of ways to really take these products and turn them into sequestration. Namely, we're looking at not just the products you've seen here but biochar, a coking coal replacement I mentioned. We have a supplier in Mexico who said they would take all we could provide because we can use hydrothermal carbonization using our own biomass to actually bring it to a point where it can be used in coking coal. And I mentioned the microbes piece. So we're really excited about this biorefinery process, and also that we've really secured collection from across the Caribbean. So from a lot of resorts in Mexico, the Mexican Navy, we're collecting from Barbados soon, where we have a remote collection business model where people from all over the Caribbean can actually treat the water, get the water out locally, create biostimulant there. We tell them how to get rid of the arsenic, and we supply them with some additional additives, and then they sell it there and ship us the pulp so that we can make this a Caribbean-wide response to the sargassum problem. We can actually turn it into higher GDP for those countries. And so we're excited about all of that. We're thinking a lot about the carbon nature of this. We would love to get input from everyone that would like to provide it. We're thinking about how we really move forward with the carbon savings. And lastly, I'll just add, we're backed by the founder of Nest, Matt Rogers, through his group called Insight, Baruch Future Ventures, which is out in the Bay Area, Vidya Ventures out of Germany. They're really seeing this move towards sustainable supply chain. And then the former managing director of Estee Lauder Germany, who's bringing us to the product and packaging divisions there at Estee Lauder. So we're trying to find the best places to put all this. Our biggest challenge right now is to prioritize it and make sure that we have the best carbon impact possible. We'd like to use the ocean to do so, possibly if we can sink this in a responsible way. There's certainly ways that can be explored as to how to sink the sargassum. We're looking at ways to ranch more of it, of course, which has been the thinking there has been started by ARPA-E and some people on this call. There's ways we can biorefine it, we think, that are creative. And so we want to really come to the best solution. So we're only 1 year old. We'd love your input, and thank you for the time, and thank you for the invitation, Paul.
Great. Thanks very much, Jeff. Really exciting stuff. We've got, well, let's open up for discussion, and then we want to make sure we then get to Eric. So Stephen, please go ahead. And if people, I should have said earlier, if people can introduce themselves when they make an intervention, that'd be great.
So I'm Stephen Petranek. I run a fund called Ocean Zero, which is trying to decarbonize the world's oceans, mostly the shipping component of it. But I have a sister fund called Viria that invests in clean energy. And one of the companies that we're about to invest in is called Proton Power in Oak Ridge, Tennessee. And they build extraordinarily efficient hydrolyzers and downstream engineering that turns things like seaweed into hydrogen, pure hydrogen, electricity, biofuels if you want. And the off products of it are biochar and very, very, very high quality graphene. You know, good graphene is $50 a gram right now. I think when a lot of people start producing a lot more of it from waste streams through pyrolyzers like Proton Power has, that the market price of graphene is going to come way down, but it's an amazing product. And this process can produce graphene at 1 cent a gram. So very high quality graphene. And just as an example, if you take a small amount of graphene and put it into a asphalt or cement highway, the highway will last literally twice as long. So there's a great demand for it. But at any rate, you can take one of these Proton Power pyrolyzers and put it on site where you would have a lot of seaweed washing up on the shore and process it. These little factories are not that expensive. And instead of having all these other products that you're trying to develop, like hydrogels and aerogels and plastics and things like that, you can just very simply, without any toxins whatsoever, turn this into biofuels or electrical generation right on site, or pure hydrogen. And then you get either biochar or graphene out of the process, which makes it very, very profitable to process this stuff. So there's no waste, there's no bad stuff that ends up back in the environment, and it's you completely get rid of the carbon. So I would encourage you to contact them, and I'd be happy to make the introduction for you there. It's a really, really interesting company, and I think it's going to be big news pretty soon. And it's perfect for your seaweed.
Thank you. We'll look at a couple hydrolyzers. Certainly we'll be in touch.
Well, the thing that's remarkable about this company is that every other pyrolyzer on the market, it runs at about 500 or 600 degrees centigrade, and you end up with toxins and lots of waste products. This company's pyrolyzer runs at 1100 degrees centigrade, and they're working on a 1400 degree model. And every 10 degrees you go up from about 600 degrees centigrade in efficiency is exponential. So these machines are like nothing else that's out there.
Thanks, Stephen. Good connection on that in terms of the algae availability and the volume and quantity that's coming out of this whole sargassum situation. Other questions or comments for Jeff?
Yes, this is Lena. Hi, everybody. A great presentation. This is right up my alley. I've spent the last 15 years at the forefront of material science innovation. So I think the challenge in my experience with material science companies is that there are so many applications, and the key determinant as to whether a company is going to succeed or not is the ability to appropriately sequence the rollout of different applications. And so when I work with material science companies, one of the things we look at is mapping out what are your near-term opportunities to revenue. So that's 6 to 12 months. What are your midterm opportunities in the 2 to 3 year range? And then what are the 5 to 10 year really long-term opportunities in industries that are heavily regulated, let's say like automotive or airspace or others. And so my question is, how are you thinking about the sequencing? There's so much, as you laid out in the presentation and the mapping of all the different industries and applications. What is your thinking currently about the sequencing of it, and therefore the revenue trajectory vis-a-vis that sequencing of different applications?
Yeah, thank you for the question. So a biostimulant is ready and in the market right now, and that's the very first natural one to go with because it's the first thing we squeeze out when we take the sargassum and we deal with the arsenic, et cetera. So biostimulant is product number one, and that's our 2021 revenue goals. 2021 into 2022, we're getting a lot of excitement about shoe soles and some basic products made in the manufacturing group that I talked to you about earlier. So we're connecting with several of those groups. So there's some basic kind of low tech applications that they're bringing us to. They said, quote, "This is the most market traction we've ever had in 5 years," because the story of sustainability and the product applications potential. Right. But then, so then we're moving. So biostimulant, we're doing the soles. The aerogels are getting a lot of attention, which would be probably 2022 in terms of jackets, insulation, things like that. And so we have that whole. You're absolutely right. I tell this story, and people say, "Well, your biggest challenge is you got to focus," and that's absolutely correct. And so we have the whole roadmap of how we're going to do that based on customer feedback, timelines, as you mentioned, regulation in some cases. But we're segmenting those markets and tackling them one by one. And you're absolutely right. I'm happy to provide more information on how we prioritize that. But yes, we have our own roadmap. The last thing I'll say is there is so carbon credits can be a part of this, as people have mentioned before. So we're working with a group on that. But also, eventually, we want to really be in the plastics and packaging world because that's where we can have, yes, it's the biggest market, it's low price, but our supply is zero COGS, right? So we can really play very well in that packaging and plastics market. And that's one of the big reasons we got into this in the first place is carbon plus solving the packaging plastics problem in some way.
Just an offer, I'm on the board of arguably the most sustainable footwear company that I think would really, and they have an innovation lab. They're consistently innovating on the material side. So I think they would be very interested in the footwear application. I'm also on the board of a packaging company that's working with some of the biggest brands like ConAgra and so on engineering specific solutions for different types of food packaging and other packaging. So happy to connect on those two applications.
Wonderful. Thank you, Lena. I will certainly take you up on that. Appreciate that. That sounds exciting.
Great. Excuse me. Well, this is what we like doing at the World Ocean Council, is helping connect people. So really, really good to have all these interventions. If there's not another burning question, I'm just conscious of the time and really would like to make sure we have plenty of time for Eric as well. So I propose that we go ahead to Eric and then follow up with his questions on his presentation and then open it up more generally again. So if you can unshare, Jeff, and then we'll go over to Eric.
Sorry, I thought I did. Am I still
Oh,
sharing?
no, you're right. You're good.
You're
Yeah.
good. Let's
Over
see
to
if
you,
you
Eric.
all can see my screen. Let's go present. Okay. 1 second. Hello, everybody. I'm Eric Matzner, co-founder of Project Vesta. I see a lot of familiar faces on the list here, so hi to everybody. Try to keep it fairly quick. Just give you all a rundown of what we're up to. Coming to you from down in the Caribbean at our currently undisclosed island where we're working on our pilot project. So let's see out the window. I've got a beach right there. That's not our beach, but we are staying close. You know, as you all know, the models currently already are relying on gigaton scale carbon dioxide. I don't know if anyone on here needs to be convinced of that. Obviously, we need net zero, but we really need to go negative. One of my favorite papers is in negative emissions. What's our role in the Paris Agreement from the European Academy of Sciences? Oops. And basically in the introduction, it says, well, we're relying on these technologies, but we haven't invested in them and developed them. So if these have a failure, then we could condemn humanity to a dangerous and woman world. So that's essentially kind of the ethos of what got me into this field and what got this project started. As you all know, we need to not only significantly reduce our emissions to a level that was essentially greater than what occurred during the shutdown of the peak of the pandemic every year for the rest of the decade to hit the 2030 targets of the Paris Agreement. So essentially, we must start removing much sooner than before the middle of the century. So the good news is Earth has a way to store carbon. And in fact, 99.9% of carbon is already in rock, which is essentially the lowest energy state. All carbon will eventually essentially end up there as it goes through a process. It's visually seen here in the White Cliffs of Dover. So you can essentially understand that if we can make this geological, millennial, millions and billions of year scale process occur a tiny bit faster, we can fix the 1/3 of the extra CO2 that makes up that 0.0009% of the atmosphere that's causing all of our trouble. So based on that and some other research, such as looking at when ultramafic and weatherable rock and silicates have been exposed near the humid tropics, it's caused an accelerated weathering events over millions of years that led directly to global cooling. So if you actually take a look here, we're gonna see in a second, I don't know if we have the time to wait for it, but basically you'll see like India start moving up into the green, which is the equator, around 50 million years ago. And once the Himalaya and Tibet Plateau start to weather, here they go now, where they turn orange as a volcanic suture, you'll see an ice age occur on the poles. And so that process, there's all that ice. So essentially, and still going, there's where we were today. So essentially what we're doing at Project Vesta is just modeling Earth's natural carbon removal process, the carbonate silicate cycle, which is the longest long-term carbon cycle, it's also known as, but essentially just making it a little bit less long. And some of those great presentations before me touched on very similar processes about how carbonic acid, CO2 goes into the water, becomes carbonic acid. That carbonic acid then mixes, basically, it's complicated chemistry in technical terms, but you increase the buffering capacity of the ocean, turning more CO2 into bicarbonate, trapping the carbon, which eventually turns into calcium bicarbonate, which is essentially put into the shell of corals and the skeleton of corals and other marine calcifying organisms. And so we've gone in with a rock, I don't know if you can see my video, but there's a big crystal version of olivine or olivine, however you like to say it. And that's the crystal version known as peridot. And essentially this rock, 1 ton of it can remove on a stoichiometric basis 1.25 tons of CO2. On a real world basis, considering the life cycle assessment of the work, we're looking at a 1-to-1 ratio. The good news is that this is one of the most abundant minerals on Earth, making up over 50% of the upper mantle. And there are near surface deposits on every single continent, stretching kilometers wide and thousands of meters deep sometimes, of unadulterated formations known as dunite, which is 90% pure olivine. And so essentially there's ample of this rock. It's currently only used in industry and blast furnaces and some other places due to its casting abilities and its temperature stability into the thousands of degrees. So the idea is to make what is essentially a bespoke rock that's charged at $150 a ton and bring its extraction down to the economic cost of it, which is around $10 or so. But I'll go into the price and stuff in a minute. But essentially, some astute researchers realized that olivine on the surface, it basically forms a crust and becomes slow to weather. And the humidity and water can't get into the surface. And essentially, during freezes and melts, new rock is exposed that then on geological time quickly weathers. So essentially all weatherable olivine that's exposed has already weathered on geological time. But if you put the olivine into motion, and this is where the real innovation is you can cause collisions that not only cause surface abrasion to remove the coating, but actually grind the rock down so that it dissolves at rate, dissolutes at rate much faster than any model predicts. So you can see some like 2 to 3 millimeter grains in the picture there that were then after 2 months just on a desktop rotary shaker made into like sizes that would weather in a matter of months and low number of years potentially. Here's another study that looked at them in a flume, just showing the motion. You can see essentially those breaks in the graph or when they on the weekend when they stopped the flumes. And you can see that the pH as the rock is in motion is going down as it essentially causes a reaction that raises the alkalinity and sequesters carbon or removes carbon from the acidity calculation. And so when they stop, more CO2 is entering from the top of the flume on the weekend, and they started again, and you see it rapidly increase the weathering through that abrasion. So based on this type of research, as well as some other research on mine tailings and other crushed olivine and areas where rivers have run through deposits and numerous lab experiments, it became pretty clear that there was a model in here where if you can get olivine and put it into motion in a low energy way, that you can dissolve, have it suck up carbon and increase the alkalinity at a rate that can be relevant to human timescales. So essentially, that's what Project Vesta is a group working to develop this science to deployable levels and investable levels. The idea is with 2% of the world's shelf seas and an area of like 7 kilometers or 8 kilometers cubed of olivine, which is doable based on our current mining of aggregates and other sand, which is, if you are curious, around 50 billion tons of aggregates and rock a year. So we only would need, if you want 10 gigatons, you just need 10 gigatons of rock, which is actually fairly doable with existing technology and nothing new needing to be developed. So we essentially were looking at various techniques that could scale to gigaton levels and beyond. I saw this chart in one of the papers cited in the, it's a potential, it's a great analysis. It's the potentials, I believe, part 2 of various techniques. And it's sitting there right in the center, enhanced weathering, yet I couldn't find any active projects putting this into use. And I believe that the numbers here on the cost are way wrong, as well as the scale. And so that essentially was in this analysis of looking at economical, scalable, and permanent solutions, turned out that this enhanced weathering in the coastal environment with olivine fit into all of these. And so we determined we could get it below $25 a ton. It's permanent on the thousands of years in solution and millions to billions of years as rock until it comes out in a volcano in the future, and that it avoids some issues in terms of competing for arable land, water, and generally energy and other use cases of other technologies that are proposed, such as BECCS and things like that. So, and even DAC. So basically, we are kind of in this middle. If you're familiar with the technological readiness scale, this generally the first three, TRL scale is 1 to 9, 9 being commercially available, 1 being a concept. Basically, this is the basic science of what would be done in a lab and government funded. The 4, 5, 6, the in situ pilot sites and project demonstrations are essentially where we are and what we're working to essentially bring this across the chasm to deliverability for global scale implementation. And so we believe that there is just a finite pathway of experiments that can be done to demonstrate this, that it's safe, that it's effective, and that it's desirable to be implemented. So you can see economically, this type of technology and process is far below nearly every other permanent process, essentially. And this also has co-benefits in terms of alkalization, increases, diatom fertilization through the silica, free silica that comes off. Yet we don't even factor any of that into the value of it. Simply looking at carbon market prices and the process of development, I've personally visited olivine mines during the pandemic, and I'll tell you, it was pretty wild to be in a mine looking, surrounded by all the olivine and telling me that they could get it out of the ground for $3 a ton. So our numbers, I would say, are conservative based on the type of large-scale mining that would be done. And the basic most expensive costs are transport and energy costs. The milling is not even that big an issue either. So if we can, the basic models that we've been inspired by and that we're putting into use essentially try to limit the distance from the mine to around 300 kilometers. Mind you, all of this data is done with CO2 emitting trucks, diesel trucks, and none of this has been updated yet, which is a project that we're doing this year to using all hydrogen powered, green hydrogen powered or electric trucks, which are all coming online around the same time we plan to be implementing over the next decade. So essentially, right now we're around 95% efficient if we use a mine within 300 kilometers by truck and or say 1,000 kilometers by ship. So it's effective, efficient, etc. The question is, why has nobody done that? Which is why we are existing and why I'm here on an island working on it. And so last year we pre-sold our first weathering that will come from our pilot projects through Stripe. We were one of the 4 companies they selected. We've got our pilot project in progress. Our team has grown. We've surpassed $2.5 million of funding for our first pilots. And we are on our way to partnering and looking towards the next parts of our scientific roadmap and whatnot. The eventual idea is to develop an integrated assessment model for coastal enhanced weathering that takes into account the maximum amount you could weather safely based on that rate, based on the life cycle assessment, and essentially give you a net cost of carbon removed per dollar. And develop that and use that model as a basis for certification. By the way, the person for Vera on here, please message me. I'd love to chat because we've grown our team dramatically over the last year. And we have some of the top scientists in terms of the coastal enhanced weathering ecosystem. We're bringing on some of the top geologists, geochemists, modeling people, and a team of entrepreneurs and others with experience in bringing things to market. And so, as I said, we've raised the money. That's kind of where we are now. And now we're getting ready for phase 2, which is a large and increasingly larger number of experiments to be deployed. And we're looking to raise $20 million to help get this technology out of this chasm, ready to be deployed in the market, and then scaled across the entire world at gigaton levels by hopefully the end of the decade and beyond. So that's Project Vesta, and I'm happy to take any questions.
Great, thanks very much, Eric.
This is my email is Eric@Project Vesta. You can use the contact form on the website, projectvesta.org, or just hello@Project Vesta, goes to the whole team, essentially.
Questions for Eric? Peter.
Yeah, Eric, that's well done. Very interesting. You've made a phenomenal amount of progress. Quick calculation to operate at gigaton levels would require about tens of, at $16 a ton would be, I guess, roughly $20 billion a year. Where would those offsets come from?
That was the idea. Yeah, that's the idea of looking at the carbon prices in the EU, looking at the way they scale up over the century. So we're clearing basically any carbon markets fees. We have numerous like we sold at $75 a ton to Stripe already. The idea is there is a premium on permanent sequestration that we are hopefully going to be able to receive. But even without that, we should be below even today's carbon prices. So that would give you right now nearly $14, $15 of profit per ton removed.
That's great. Now, is this going to be workable with the, this is for the voluntary market, for the compliance market as well?
Yeah, we are. That's some of the stuff we're looking at this year. We're looking to bring on policy people, government relations people to get into the those markets. Right now, we're really like laser focused on just deploying these, building our scientific roadmap. It's a sort of, if we can deliver this at scale, then I don't think we'll have any trouble. If it's, as we expect there to be low to no issues that aren't remediable with, for example, nickel that could be in trace levels below 0.5% or so or something in the olivine, that it binds in a certain phase and it becomes not bioavailable. So we really just need to work out the kinks and demonstrate the models are somewhat valid, because the deeper you go into the science of the modeling, there are no sophisticated physics-based collision models to generate weathering rates. The good news is we, through some partner funders, we have some independent research going on in a carbon accounting framework in the Netherlands. So we are working on some those models. We have to basically build the verification system, build the physics models, and then include and essentially the technology to enable the deployment.
Phenomenal. Thank you.
Thank you.
Thanks, Eric. Phil has been waiting to jump in. Phil, go ahead.
Thanks. Just on the ocean acidification issue, so you're beneficial to that issue, am I correct? And the second question, that would be near shore, where are you spreading olivine all across the oceans? How are you dealing with the ocean acidification out thousands of miles offshore?
Well, yeah, so at the moment, we are raising the total alkalinity and the dissolved inorganic carbon in the ocean. So, we, at the moment, due to us not having our own research in the ocean showing this, we're not really making any claims on acidification. We're purely about carbon removal, but generally, yes, we are alkalizing the nearshore area. But luckily, there's many people, like the previous presentation is in the open ocean, 2 presentations ago is in the open ocean. So we're not the silver bullet. This is a silver buckshot, right? It's going to be all of these approaches, and we're not trying to do everything. We do want to be prepared to scale up if we were needed for, suddenly need more than 10 or 20 gigatons a year, because we've caused some serious catastrophic issues. But we're a part of the ecosystem. We want to be, a good member of the ocean community, and not try to lay claim to all the areas. Also, by working in the area of economic activity of the countries, we're not technically, at the moment at least, under the London Protocol or things like that. So part of it is being by the shore. We work with the local individual countries to get their consent of the local population. We're very big on social license, and we have community relations and things are what we're working on now, is learning how to bring this process to the people, showing them the benefits of increasing, like lowering the stress on their corals by, helping the the metabolic stress levels go down, which is what acidity can cause to the coral. So that kind of thing. Yeah.
Thanks, Eric. If we could go to Stephen and then Brian, and then we'll open it up to a broader open forum here. So Stephen and then Brian.
Oh, you're
Stephen's
muted.
Thanks for the presentation, Eric. I was actually aware of Vesta, and it's a very cool idea. I'm curious about the practical application of this. Are you dumping stones from a ship? Are you spreading sand on shores? I'm curious about the costs that might be involved in actually getting this into the water, and what local communities might feel about that.
Yeah, great question. So we do have a working group within our team in terms of like a 1 million ton deployment, like theoretically what that looks like. My personal opinion and strategy would be to minimize the loading unloading of the olivine. And looking at the infrastructure and the cost, like there are union fees, and it can be very expensive to load and unload, and time consuming, and especially volume. So my ultimate like vision for 1 billion ton deployments would be to like find some very large mines, build a slurry that are near the coast, build like a slurry pipeline, not even have to load the ships, just like a gas station, essentially just filling these mega carrier South Africa, Cape ship, 400,000 ton mega carrier load ships that are self-unloading with olivine, bringing them to like an area like off the shore, having a fleet of rainbowing boats. If you Google rainbowing beach nourishment, there's in the Gold Coast of Australia, they have these ships that basically spray out and they send it towards a certain direction. So the idea for me is always to kind of be nature inspired and bio inspired. And so like mimicking like what would be in that area, the maximum turbidity in the worst storm of the year, for example. And maybe instead of like how the earlier we were talking about like finding single beaches, like just doing one run across the whole coastline and not coming back to that area for like a year. Where it would have very little effect, wouldn't even be visible in the pore sediments. It would just be like weathering away in a layer that is essentially invisible to the naked eye, and invisible in terms of the signals in the pore sediments, because there's bacteria and different things and symbiotic organisms that we don't want to have any negative effects on. We want to be like just as passive as possible and just simulating the natural turbidity that could put down some sediment. We don't want to cover corals or anything like that. So we're still learning how to do that. We're engaging with beach nourishment companies. We're engaging with various stakeholders who have experience deploying millions of tons of sand into the ocean, so that we can figure out how to do that in a way that is solely net benefit.
So are those costs of slurry pipeline to large ships and then offloading it onto smaller ships and spraying it into the water, are those costs included in this cost table?
Yes, essentially, like, I mean, I think this is what the top right is one that was made by us. So I visited a mine and they basically said, we can take they were 70 kilometers from the coast, and they could take, I think, a 30-something ton dump truck to the port for $20. And then it was like another $20, $10 or something at the port to get it onto the ship. So that, you know, that on a one dump truck scale or one shipping container scale is essentially like below $100. So the idea is that at scale with no loading and unloading, we could probably go below $10. However, my team would not like me to say that because we're trying to be very conservative with our numbers. But if you look up mining engineering textbooks and actual some of the land weathering work, I could send you the numbers afterwards if you'd like, but they have mines that are $1 extraction. This mine I looked at, they were like, just put dynamite here, 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 and here, and you'll drop down, you know, hundreds of thousands of tons in one day. You come by with an excavator, put it on a conveyor belt, take it to a hydro dam that could power our grinders, and load it onto this train that's about to be built. So like there are entire ways to clear the life cycle down, to build our own railways. And I like to think of these. I love reading about mega scale projects in space and things like that. So, but these things are solvable problems that are being done in other mining industry processes. So we are just looking to custom tailor those, whether to optimize for the lowest cost and the lowest footprint.
We might go ahead and jump to Brian if we can, Stephen, as the
Yeah.
time is running short.
Yeah,
Thank you, Paul.
I'll email you, Eric.
Please do. Yeah, if you could tell, I'm happy to discuss, especially the future stuff, because I'm so focused right now on getting one grain on the ground here that the billion ton is a twinkle in my eye right now. So just trying to get us there is extremely difficult to get over this hill. So we are working to push forward this technology safely and as fast as we can to get to that.
Hopefully it's a hill of olivine. Eric, thank you for your presentation. And I'm curious, can you give us some feeling for the fraction of olivine that makes it from these rainbow ships to the beach, let's say, and then perhaps more importantly, whether you're putting the sand on the beach directly or from these ships, then what fraction of the olivine stays at the coastal intertidal area long enough to actually weather down, and what fraction of the sand gets transported away? Do you have a sense for your ability to produce fines before the olivine actually gets taken from the beach and, let's say, taken into deeper water?
Yes, some of these questions are TBD, to be determined. Essentially, right now, I'm looking in our experiment to essentially model how we will deploy in the future so that people can say, well, you put it by hand here and now you want to rainbow it, so it's not the same. So I am looking at how we can spray on our pilot project, for example, because we right now are just monitoring where we have 2 bays. One is where in the green there is essentially the experimental bay, and the other one is going to be a control. So we're measuring to get the signals of over time and just establish a parity in signal between the bay. So it's a before and after and a parallel design. So I've tried to make this most robust experiment possible so that nobody can say, well, what about this? How do you know this is not a seasonal variation? Essentially, what we're looking at, as long as it's a shelf sea, Brian, it should actually continue to weather in that transport. The worst possible case is that it gets buried and then doesn't weather, and so essentially, as long as it's exposed and not just that flume experiment, I have a video in one of the other tabs, but it is moving so slowly, you'd be surprised that it's able to cause that that weathering reaction. But it's just, the silica of the olivine is a tetrahedral structure that when the water gets in, it just slides across each other. So the idea is, as long as it doesn't get buried, that's good. We're also looking to target for each site. So we have to go and look at the sample and look at the sediment and look at the pore size. And first we have to be larger so that they're not suspended in the water, essentially, which is ocean alkalization directly. But we want it to be large enough that it can collide and stay without suffocating the stuff below it, depending on how thick the layer is. So these are all things that are dials that we're working to figure out the optimal version for, which is what we're raising the $20 million for, is 20, 50 experiments in different locales on ecosystems, temperatures, turbidity, which, I hope to spend the rest of my life visiting all those different beaches to see them. But we don't have all those answers right now, and I'm not going to pretend that we do, but those are essentially if you Google the sand motor in the Netherlands, they basically built a giant, I think it was 20 million square meter pile of sand underwater. And then they knew how it would model down the coastline to spread itself over the next 10, 20 years. So it's possible we do a sand motor style where we actually put it in one spot and let the natural currents distribute it at a rate, like I was saying, that mimics the natural sediment transport that we as humans have interrupted by damming all the oceans and filling them with other chemicals instead of the sediments that would be doing this process naturally.
I'm wondering if there's a power density for dissipation approach that would basically relate the power density either on the beach or in the deeper water with the erosion rate. and you could probably tie those two together. And I wouldn't be surprised if there may be some beach transport papers that might relate this, and you might be able to relate that dissipation density to your erosion rate.
Yeah, I'd love to. If you want to, I can connect with the science team if you'd like to like hop in and they can answer that more fully. You can actually email science@Project Vesta. It's mostly internal, but that will go to a lot of people. We have a Slack channel too that I can let you in for kind of external people to kind of quiz around, because we are doing this in like the most open source way we can to like basically build the playbook for how to deploy this, and then potentially have a verification system and on top of that, where we can, encourage deployments, but make sure they're done properly. We're starting to get some worries of like the nuclear, secrets kind of thing, where if it gets into the wrong hands and they just like say we're selling carbon credits and just dump a bunch of rock and kill it, it could really go the wrong way. So we're trying to figure out, governance and things like that, and how to self-govern. And some of the people on this call, I think, are in discussions with us on that. And there's this great brain trust that we are hoping to put to use to do this project. And we really love any help and any ideas.
Thank you.
Thanks very much, Eric. We have gone through some great examples here of what's really happening at the forefront of the business world, and I hope this has been really as valuable and interesting to all of you as it has been for me. I think this is really proving the interest and the need here to get to help create the platform and advance all of these collectively. And I'm seeing from the point of view of the World Ocean Council, certainly some of the cross-cutting aspects in terms of engaging the shipping industry, the dredging industry, ports, and a whole range of other players in the maritime industries, as well as, of course, the investment community, as we work collectively to develop and deploy these ocean carbon dioxide removal technologies and opportunities, and really build the businesses and engage the investment community. Let me just go to share screen here. And so as we do this, and we're not going to get to this today, of course, as we're just about out of time for our 90-minute allotment here, but really looking at how we can build this community through the roundtable and the overall ocean restoration, carbon dioxide removal community here. And so what we'll do is pick up this in the follow-up from the last year's 2 meetings and this meeting, to really then look at what is the way forward in really creating this sort of platform and this collective, the value and the benefits of a collective approach to this. We did last time get into some of those discussions, and we'll be a little bit behind getting that summary report out. But we want to move forward with the developing the steering committee for the roundtable group, and just trying to advance here and really, I'll send this around. We won't get into this now, but really looking at who we're pulling together here and for what reasons, and develop this this range of potential. I'll just jump ahead here quickly. Potential outputs and developments to really advance our collective efforts and those of the individual companies. And so with that in mind, I'd really like to thank all of you for being here, and thank Eric and Jeff and John for the presentations. I'd really like to highlight especially John Ridley and Ocean Nourishment, because they've been a World Ocean Council member since 2012. And so the reason the World Ocean Council is able to do what we do is because we do have the support and involvement of member companies. And that's been an essential building block for developing the global business and investment network that we have, that's focused on ocean sustainable development, and now increasingly, and since 2012, on the role of ocean carbon dioxide removal and ocean negative emission technology. So we'll keep this moving. It's not surprising that we got into really into some detail here and went through all of our time. And this is what we'd like to continue to do, is highlight those companies that are moving forward with this. I'll be reaching out to some of the other companies that are on the call here and otherwise to have the opportunity, if interested, to present their work and progress and then we can also, we would like to have then moving forward some of the investors given the opportunity to really express their interests and concerns and challenges and the opportunities that they see in the ocean carbon dioxide removal space and ocean restoration space as we continue to advance this. So unless there's any burning comments to close off, we're right at the 90-minute mark, and I propose that we go ahead and stop here to respect everyone's time commitment, and we'll plan forward with our call for next month, and be engaging with those of you that have indicated previously that you're interested to be on the steering committee for the roundtable, to help us get a bit more structure and advanced planning into the process here, as we continue on with this collective journey. So with that, I'll say thanks everyone, especially to our speakers and especially to John and Ocean Nourishment for being a World Ocean Council member all these years, and encourage others to consider getting involved more directly with the World Ocean Council. And we will we'll be in touch with all of you to plan forward for next month's meeting and sending materials in advance of that. So thanks everyone.
Great, thanks Paul. Thanks everyone.
Thank you, everyone.
Cheers. Thank you.
Thank you to the whole community. I think, we need to involve every aspect, all these industries together to make these type of projects a reality. So thank you, Paul, for hosting this forum, bringing together the different intersections. I'd actually love to see presentations from the different business partners, of what their industry is offering and what they're able to contribute potentially, and like what they want to contribute, or where their current initiatives are that could align with other projects. And that resource would be excellent for anyone in this space starting a project, to know directly where you can connect and where into the company you can go to make that connection. It's really hard to just approach a shipping company or approach a marine company without knowing the relevant person always. So thanks.
And I think that's, Eric, that's really, the role we can play here at the World Ocean Council, because that's the community that we know well: shipping, dredging, coastal construction, etc. So I think drawing together a collective business leadership coalition around this from not only you businesses that are working directly on CDR, but those as you say, those partner companies that have a role to play. So we put that whole business package together and look for the economies of scale. So
yeah, great. Thank you.
All right, thanks everyone.
All right, all the best. We'll be back in touch.
Thank you, Paul. That was great.
Thanks very much, Brian. Great to have you involved. And
Oh, likewise.
we
And I'm
need to
just
pick up a
curious.
discussion directly at some point as well.
I think that'd be great. And let me know if there's an opportunity to contribute on the steering committee. I'd be interested.
Great. Make a note of that. We're really getting this all organized just now. So thanks for the offer.
Great. And is there a WOC membership option for nonprofits?
There is. So we have sort of a scientific research and academic institutions is more or less that sort of piece. So that's be happy to have the Climate Foundation get involved.
Yeah, let's explore that further. That sounds great. And thanks for hosting these.
Okay.
Excellent.
Sure. I'll send you that information.
Great. Thank you. Thanks again, Paul. Good to see you.
All right. Likewise.
Take care.
Take care.
Bye.
Bye now.